chemistry department was instrumental in developing some new mixed metal sulfide clusters. The catalytic and characterization work that I'll be talking about was done at the Department of Chemical Engineering. The goal of this work is to better understand the effects of promotion in sulfide in supported catalysts, and our method is to study the activity of organometallic clusters on different supports. We'll be looking at promotion. To study promotion, we'll be looking at mixed metal clusters. These contain more than one type of metal atom. The binary system that we're going to be talking about is the ruthenium-cobalt system. We'll be talking first about the cluster structure and synthesis, then we'll look at some characterization work and finish up with kinetic measurement work. The characterization work is important because it reflects the stability of these clusters at elevated temperatures. That's important in understanding and interpreting the kinetic data. This is the type of cluster we're talking about. All of them contain 3 metal atoms, in this case cobalt in blue and ruthenium in orange. These are bonded by metal-metal bonds and capped by triply bridging sulfur ligand. The unshaded ellipsoids surrounding this are carbonyl ligands. These are the 4 clusters we'll be dealing with. The first all contain 3 metal atoms. The first contains 3 ruthenium. The second contains 2 ruthenium, 1 cobalt. The fourth contains 2 cobalt, 1 ruthenium. The last contains 3 ruthenium. So these form a series as we step through the series one by one. One by one, the rutheniums here are replaced by cobalt until we have a cluster containing only cobalt. There are other ligands present here. The first 2 contain unshaded some bridging hydride ligands. The last contains an additional bridging sulfur ligand. For simplicity, I won't refer to these in the future by their complex chemical formula. I'll call these according to the number of cobalt atoms they contain. This is then the cluster containing 0 cobalt. This is the cluster containing 3 cobalt. This last structure here is not strictly correct. This molecule exists instead as a dimer, where the bridging sulfur here forms a bridge between 2 clusters to form this 10th dimer. The clusters are made in 3 separate reactions in solution. The first reaction is for the formation of the ruthenium sulfide cluster. This is a rapid reaction between ruthenium carbonyl and H2S. It takes place at moderate temperatures and pressures, and high yields are obtained after only half an hour, about 75% yields. The ruthenium sulfide cluster is the starting material in the second reaction with cobalt carbonyl to form the mixed metal clusters. This is a slower reaction, takes place at elevated temperatures and pressures. Yields are pretty low, maximum yields after about 12 hours of about 15 and 30% respectively. The last reaction here is for the formation of the cobalt sulfide cluster. This is a relatively slow reaction. Again, this takes about 4 hours to get maximum yields. Yields are pretty low, but yields are fairly low, but it can be easily scaled up to provide large amounts of the cobalt cluster. Characterization of these was done in the IR. These are spectra of the cluster containing only ruthenium, both in hexane and in solid phase. These are the carbonyl stretches of the cluster. The totally symmetric stretch here at 2119 is retained in the solid phase. Some of the other peaks are shifted or split in the spectrum. During decomposition at elevated temperatures, the spectrum broadens here at 150 degrees. The broadened spectrum is retained to about 250 degrees at high temperatures. the clusters degrade and transmission falls very low levels. This is for the ruthenium-only cluster. See similar broadening. This is the same cluster in a different region of the infrared. See the same type of broadening at 150 degrees, but the peaks are more widely spaced and does not have such a pronounced effect on the spectrum. We see stability retained to about 200 degrees. 250 degrees, we see some restructuring, and at 300 degrees, the clusters have completely degraded. Other clusters exhibited, the other clusters I won't show the information for the data for, but they exhibited similar profiles. Supported catalysts were formed from these clusters using solution impregnation or pore volume filling method. Methylene chloride was used as a solvent. Both gamma alumina and carbon supports were used. Two loadings were used, rather arbitrarily chosen as the molar loadings of 5 and 10 weight% tungsten support. After impregnation, the methylene chloride solvent was removed by evacuation. After the evacuation, then uniform particles were made by crushing and sieving. The carbon was not cohesive. We couldn't press it into pellets for making the uniform particle sizes. It was used as received as 20 to 50 mesh particles. The supported clusters have broadened CO stretching spectra. This is for the cluster containing only ruthenium at 10% loading on alumina. Only the totally symmetric stretch here at 2119 is retained or visible in the infrared. The totally symmetric peak stretch is retained up to 200 degrees. At higher temperatures, the cluster loses its integrity. We observe unsettling CO on the metal surface. We also see in the spectrum the presence of methylene chloride solvent, which is mostly removed during heating. Other clusters exhibit similar profiles, which clusters are stable at 200 degrees C. We didn't look at the infrared spectrum of the carbon-supported catalysts. They didn't transmit and could not obtain spectra. Summarizing then the decomposition of these clusters, we found that the unsupported clusters were stable at 200 degrees C, and that no clusters remained at temperatures above 250 degrees C. Those clusters supported on gamma alumina were observed up to 200 degrees C, but completely degraded at temperatures above 300. I'm going to shift focus then now and look at the kinetic measurements part of this talk. We've already looked at the stabilities of these clusters and established that they're not stable at elevated temperatures. We're going to look at two different regimes for catalytic activity. Catalyst sulfide at 400 degrees C, where we would not expect to retain the structure of the cluster, and then unsulfided cluster catalyst looking at the initial desulfurization rates. In this case, try to minimize decomposition of the cluster by skipping the sulfiding step and looking at the initial desulfurization rate, especially at low temperatures, where we expect to retain cluster structure. Kinetic measurements were performed in a automated microreactor. The packed bed of catalyst was loaded in the quartz tube. Thiophene reactant and hydrogen flowed over the catalyst, 30 mils per minute. Analysis of the products was made by gas chromatography, and products were identified by mass spectrometry. This is the activity data for the cobalt on carbon at 10% loading catalyst. This is sulfide for 2 hours and a 10% hydrogen sulfide and hydrogen mixture. After the 2-hour treatment, we began to record measure the catalytic activity expressed as percent conversion of thiophene over the 12-hour reaction period. This value here at the end of the 12-hour reaction period is the activity which we'll report for comparison of the different clusters. This is the catalytic activity of the sulfide clusters, 10% loadings on carbon, 400 degrees C. The the clusters are expressed along the x-axis, as I said before, according to the number of cobalt atoms they have. This represents the cluster containing only ruthenium. This represents the cluster containing only cobalt, and these are the mixed metal clusters. This graph shows that the mixed metal clusters were less active than the pure component ruthenium, cobalt, and catalytic. At both loadings and at both supports, we observe a similar trend where the mixed metal catalysts here are less active than the pure component ruthenium and cobalt, with the exception of this point here. This also shows that the carbon-supported catalysts are more active than those supported on alumina. This could be due to a surface area effect. But nevertheless, the important thing here is that we're observing low catalytic activity for the mixed metal clusters. This is a surprising result. I would expect perhaps to observe at least catalytic activity here of the pure component ruthenium and the cobalt and ruthenium components of the catalyst that could be falling along this line, perhaps even seeing some sort of increase in activity due to promotion. That's not what we observed. We observed low activities for the promoted catalyst. Some molybdenum on carbon reference catalysts were also synthesized, these using a molybdenum organometallic cluster, these being more representative of what might be used in industry. On carbon, this is again 400 degrees C sulfide catalyst. The carbon-supported cluster catalysts were more active than the reference catalyst is shown on the bottom. Catalytic activity for the alumina-supported catalyst was lower, and also we see that in this case, the molybdenum on alumina references are more active than those clusters containing cobalt. Ruthenium retained a very high activity on alumina. In fact, at all loadings on both supports, ruthenium was, in all cases, the most active. The ruthenium-only cluster was the most active catalyst. The primary products of desulfurization were butenes. Smaller amounts of butane were also observed. This could be a reflection of the hydrogenation activity of the catalysts. Here on carbon supports, you see the ruthenium has a very strong hydrogenation activity, and those catalysts containing any amount of cobalt have very low selectivities for butane. Selectivities for butane on alumina were much lower. Again, ruthenium exhibits the highest selectivity for butane, while those catalysts containing any amount of cobalt are much less selective for butane formation. This is the activity data for the sulfide catalyst that I presented earlier. I'm presenting it now because it kind of brings together some of the activity data that I've presented so far for sulfide catalysts. As I said before, we know that these clusters are degrading. We also know that the mixed metal catalysts, instead of showing the activity of some of their components falling along a line such as this, we don't observe those promotion or even some of those activities. We observe low activities for the mixed metal clusters. A possible explanation for this is a model in which, after decomposition, the cobalt present physically or in some other manner masks the catalytic effects of ruthenium on the surface. The catalysts containing cobalt have activities approximately proportional to the amount of cobalt present. This type of model in which catalytic activity of ruthenium is mapped is supported by the selectivity data. Ruthenium, again, is very selective for butane formation, but the catalysts containing any amount of cobalt are uniformly non-selective or less selective for butane formation. I'm going to switch now to the second part of the kinetic data, looking at clusters which have not been sulfided, and we can try to minimize decomposition of these clusters. This is activity measured without sulfiding, only bringing the clusters up to reaction temperatures, and then allowing the catalyst to stabilize for 10 minutes, and then measuring the sulfurization activity. In this case, see at 150 degrees, low temperatures, the mixed metal clusters are more active than the pure component ruthenium and carbon clusters. At high temperatures, the familiar low activity of the mixed metal clusters is observed. Intermediate temperatures, we see some transitional transient activity. 5% loadings on carbon. We also see high activities for the mixed metal clusters at low temperatures. High temperatures, the familiar low activity for the mixed metals is observed. Also on alumina, 10% loadings. We see very high activities for the mixed metals only at low temperatures. High temperatures, again, they're less active. And finally, this is at 5% loadings on alumina. You see, again, the mixed metals are more active. We observe some type of promotional effect at low temperatures, which is degraded at higher temperatures as a result of structural reorganization. I might comment that this is a logarithmic scale. These represent some significant differences in activity. It's interesting that between this point and this point, there's between 150 degrees and 350 degrees, there's less than an order of magnitude difference in activity. Summarizing then the kinetic measurements that we did, we found the sulfided mixed metal clusters were less active than catalysts containing only the pure component ruthenium or cobalt. Unsulfided mixed metal clusters had initial activities low temperatures that were higher than the catalysts containing only one metal component. Catalysts supported on carbon were much more active than those supported on gamma alumina. The alumina-supported catalysts were less active than reference molybdenum catalysts, with the exception of ruthenium supported on alumina. The carbon-supported cluster catalysts were much more active than the reference catalysts. Butane selectivities were high for carbon-supported catalysts than the corresponding alumina-supported catalysts. And finally, the catalysts containing any amount of cobalt were less selective for butane formation than the reference molybdenum catalysts. These last 5 points might best be summarized by stating that the cobalt is a very active HDS catalyst. Cobalt on carbon is a very active HDS catalyst, which could be used industrially, but exhibits higher hydrogenation activities than the reference molybdenum on alumina catalysts.